Now I'm going to discuss how we would look for a new law. In general, we look for a new law by the following process. First, we guess it. Then we so don't laugh, that's really true. Then we compute the consequences of the guess to see what, if this is right, if this law that we guessed is right, we see what it would imply, and then we compare those computation results to nature, or we say compare to experiment or experience. Compare it directly with observation to see if it works. If it disagrees with experiment, it's wrong. In that simple statement is the key to science. It doesn't make a difference how beautiful your guess is. It doesn't make a difference how smart you are who made the guess or what his name is. If it disagrees with experiment, it's wrong. That's all there is to it.
Much of the following explanation is adapted from Nobel Prize-winning physicist Richard Feynman's lecture on physics, a section called Electricity in the Atmosphere. For every meter you go up in the air, the voltage increases by around 100 volts, or we could say around 100 volts per yard. We can draw these voltage increases using what are called equipotential lines. Notice that the ground is negative and the sky is positive with respect to each other. According to Feynman, this extends upward to 50 kilometers, or 31 miles, where the air is very conductive. This is the case in fair weather. In stormy weather, like a thunderstorm, things are quite different, and I won't talk about that here. But if this voltage exists between your head and the ground, why don't you get a shock? The reason is that your body is a good enough electrical conductor that standing on the ground, you're basically a part of the ground. The equipotential lines would look like this. There's still effectively 0 volts between the top of your head and ground. Similar effects happen with trees, buildings, and so on. What about the electric current? A downward electrical current exists and consists of positive ions, molecules or clumps of matter that have a positive charge. These ions are moving slowly toward the ground. The current density from these ions is very small, around 10 microamps, or 10 picoamps, crossing each square meter or yard every second. So in any small area, there's not a lot of power. And that's the explanation about atmospheric electricity adapted from Feynman's lectures.
So what excites me about this project is that it's a little bit out of the box. It's an area of research that a lot of people have worked on for a long time, and people have produced a variety of different types of results based on observations, but there aren't well-established physical mechanisms to explain some of these observations. And so another aspect of this project that excites me is that it's so interdisciplinary, and that we've had to gather a group of scientists together that come from very different areas of atmospheric and space research to work together in a way that they probably wouldn't have dreamed of before. And so we have people who work on the behavior of clouds, lightning, but we also have space physicists working on the interaction between the solar wind and the magnetosphere and the ionosphere. And not only that, but we cross disciplinary boundaries in that we have to work with electromagnetism, we have to work with chemistry, we have to work with other aspects of science that are usually not combined together into one project. And so that's part of what makes it interesting to me.
So we're looking at the role of thunderstorms and electrified clouds in the global electric circuit. So a cloud doesn't have to actually be producing lightning to be electrified. And there's what we call a Wilson current that generally runs from the top of the cloud into the ionosphere and helps feed the global electric circuit. So in the typical thunderstorm setup, it's a source of charge. In the reverse setup, or the opposite polarity, it's generally a sink. So we're hoping to find some parameters of thunderstorms, like we're looking at the speed of the updraft and how much ice is in there, and we're hoping we can relate that to how strong or weak the current is.
So I'm from Penn State University and Communications and Space Science Laboratory. In that lab for the last 10 years we have been very actively engaged in development of theoretical understanding of transient luminous events in the Earth's atmosphere. So we work on a variety of subjects related to lightning and lightning behavior, lightning physics, and of course in the context of global electric circuit modeling. We want to quantify how much lightning contributes to the global electric circuit, for example, in comparison with electrified thunderclouds and electrified clouds. There is a significant controversy in existing literature as to how much lightning contributes. So in some cases, some scientists actually claim 40% of the total current which is flowing in global electric circuit is contributed by lightning. So we want to actually understand and quantify actual amounts.